3, memory accesses. So this is a very important concept. So let's look at what kind of memory accesses do we have? All right, so let's look at first types of memory accesses. There are 2 types. Actually, I mentioned that before. Instruction type accesses and data accesses. These 2 basic types. Instruction accesses. You need to load instructions of your program first. Instruction one by one after another in sequence. But some of the instructions may need to use data operands. So the instruction, when you do the operation, you may need some operands. So then you also need to load data from the memory. So these 2 types of memory accesses. All right. So then look at, details. After that, every instruction requires an instruction access. So you have to load that instruction. So there is 1 instruction accesses for each instruction. So that's very simple. But for data, things are a little different. For data, here, load or store instructions. Some instructions need data loaded or need data accesses, but some instructions do not need data accesses. So here we want to, separate these 2 different types of instructions. Typically, those instructions that need data accesses, these 2 types, load instructions and the data and the store instructions. Load, you can see, that's the data read operation. Read data from main memory. Store instruction, you can see that's the data write operations. Write data to the memory. Read and write. So these 2 are the, typical data accesses operations. All right. So these 2 also require data accesses. So you can see for this type of instructions, you need 1 instruction accesses, 1 data accesses. 2 memory accesses. For some others, 1 instruction accesses, 0 data accesses. So you can see 2 different types. This kind of detail is important when we do the calculation, when we do questions on memory accesses. So we need to consider all these cases. Next, in this case, 1 instruction requires 2 memory accesses. Although 2 memory accesses, we like to separate instruction access and the data access. They are different because these 2 different types of accesses will be processed in different ways, will be handled in different ways in cache. So sometimes we need to separate. Sometimes we do not. So that kind of details we will discuss further later. Next, measuring memory accesses per instruction. Now we need some measure. I commonly use the measure here. commonly used measure is called this: memory accesses per instruction. Yeah. So the name is long. Yeah. The whole thing is the name. Memory accesses per instruction. So think about, yeah. Memory access per instruction. For this type, memory accesses per instruction is 1. For this type, memory access per instruction is 2, right? But we need to take average. We need to consider all the possible instructions and then take the average. So it should be 1 point something between 1 and 2. 1 point something. Yeah. All right. So next, let me use a simple example. Yeah. Look at this example. If 40% of the instructions require data accesses, look at this example. All right. Suppose we have this many instructions. Okay. Suppose for convenience, we use 100. Yeah. Then, based on the assumption, 40 instructions require data accesses. So that means other than this 100 instruction accesses, then we need another 40 data accesses. Right? Yeah. So total, you can see the total memory accesses 140 memory accesses. Right? Yeah. But look at the base. The base, we only have 100 base instructions, right? Yeah. So, but the total is this many. So we do the division. The result is 1.2 memory accesses per instruction. 1.2. Okay. 1 plus, 1.4. 1.4. 1 plus this 40%. That's simple. That's simple. 1 plus that percentage corresponding to data accesses. Yeah. All right. Yeah. Next, measures for cache misses. Yeah. All right. So now we need to consider the cache miss situation. When there is a cache miss, we need some appropriate measures to measure the miss rate. Okay. So the first concept, miss rate. Yeah. So the miss rate is simply the fraction of cache accesses that result in a miss. Yep. So by the meaning, its definition can be interpreted in this simple way. Yeah. So we can write a formula in this way. Miss rate equals the number of misses over the number of memory accesses. Now you know the meaning of memory accesses, right? Yeah. Containing instruction accesses, data accesses, total number of memory accesses. Yeah. So that's the denominator. Among those memory accesses, how many misses, cache misses are there? So use that number as the numerator so you get this miss rate definition. All right. Then another concept, commonly used concept, a little different from miss rate, but also related, closely related to the miss rate. So that is called misses per instruction. See, you can see pretty close. Misses per instruction. So we can write its definition as simple as this. Misses over number of instructions. Here you can see the difference is at a denominator. Denominator. One is number of total memory accesses. Another number of instruction accesses. Only instruction accesses. We do not count data accesses. So that's the main difference. Okay. All right. But this concept, misses per instruction, usually, so for many, for typical real world situation, this number usually is a pretty small number. Pretty small number. 0.001. Things like that. Okay? Especially for modern cash. So this number usually is a pretty small number. So that may cause some psychology issue to ordinary people. So that's this situation is pretty similar to one we saw before. Remember when we learned the concept FIT, failure in time. FIT, okay? FIT, failure in time. That number of failures in number of hour, in per hour, right? Per hour. That number usually is a 0. long, many digits, then a non-zero number. That may cause people feel, so this number could be ignored. So in that situation, we multiply 1 billion to make it larger, right? Here we have a similar situation, but not as big as that. Okay? But we need to do the similar thing here. Here the situation is because that number is a 0.00 some number. So we feel we want to make the number look pretty significant. So to give people impression, you cannot ignore this number. This number is important. You have to pay attention to it. So for that reason, sometimes we use per 1,000 instructions. Per 1,000 instructions. So we multiply 1,000 to make it look like 47, 35. So when you see 35, 42, you won't ignore it, right? Because, that's quite some number. You cannot ignore it. So that's the reason for that. Next, now we want to compare these two concepts, miss rate versus misses per instruction. So what's the main difference? We saw the difference, the numerator part, but now we want to compare with some more details. Compare these two fractions. Mainly, the denominators are different. The first one, miss rate in this like this. Second one, misses per instruction like that. Now, look at the denominators. Which one is larger? Which one is smaller? The first. Okay. First, in the general case, in the usual case, general case, memory access is greater than instruction accesses because you include the data accesses, right? Inside it, include data accesses. But in some special cases, the situation is different. Okay? Special cases. Different. So what special cases? We will talk about that later. Special cases, because that related to the cache types. Cache types. Later we will see we may use different type of caches. One type called instruction cache. Instruction cache. Instruction cache means this cache is only used to store instructions. Data cache. So this cache only stores data items. Yeah. So then, third type, we call it unified cache. So this cache stores both instructions and data items. See? Yeah. So you can see all these different types. Yeah. So you will see when we compare memory accesses and instruction accesses, for unified cache, it is true. For unified cache, it is true, right? Yeah. But for instruction cache, that number equal. That number equal. Now, memory accesses equals instruction access because we exclude data accesses. Okay? But for data cache, that number less than. Memory access means only data accesses because data cache we exclude instruction accesses. We only look at the data part. That part usually smaller than the number of instructions. So then we will get less than relationship. So that's why if you need to look at the cache types. Yeah. If the cache type is not given, so then you use the unified cache. So you use unified cache, so then you can use this way. Okay? Yeah. If the cache type given, then you need to, consider different cases. Yeah. All right. So now the relationship of these two fractions. Yeah. All right. So in that case, this is smaller because denominator. So in this case, denominator is larger, so it is smaller. Yeah. All right. But be careful. There are special cases to be considered. Okay. Yeah. All right. Finally, we look at the relationship between these two fractions. Misses per instructions. Now we want to write per instruction misses. Yeah, misses, we can write it as miss rate times memory accesses. Then we separate. So the miss rate, then we multiply this fraction. We put this fraction, out of that miss rate. You can see this is another concept called memory accesses per instruction. Okay, memory accesses per instruction. Okay, so that concept, we know that. So 1.4 in the previous slide. So that one. Okay, yeah, and we know this number is between 1 and 0. Between 1 and 0. Yeah, yeah, very messy. Yeah. Anyway, yeah, yeah. All right. So here I still put the data cache here. All right. Yeah. So between 1 and 0. So you know the relationship. Okay. Yeah. First, do not get confused. These two concepts. Yeah. Second, they are related. Yeah, they are related. Oh, so now there is a common problem when you work on exercise questions. Yeah. So that is in a problem. Sometimes I give you miss rate. Sometimes I give you misses per instruction. Okay, so when you read the question, you should read carefully and use the right formula. Yeah. All right, so let's finish our 8.3 here.